So today we'll be talking about confidence interval in statistics. Okay, confidence interval. Now, when we say confidence interval, it's simply a range of values within which we are reasonably confident that the true population parameter lies based on a sample data. Now, what does that mean? What that means is that when it comes to confidence interval calculation, this is a form of statistics that in this calculation, the answer you are going to get will be two answers. Okay, for example, you see when you are calculating for mean, in calculating for mean, you end up getting a single answer. Okay, in calculating for standard deviation, you end up getting a single answer. But when you are calculating for confidence interval, you get a range of values. You don't get a single answer. You are going to get a range of values. Usually, you are going to get two values. The two values, one of the values will be lower value. We call that lower CI. And then another value will also be a higher value. We call that higher CI. That's why we say that this is a type of statistics that is going to give you a range of values. One is going to be a smaller value. The other is going to be a higher value. Is that okay? But practically, when we say confidence interval, it's a range of values within which we are confident that the true population parameter lies based on the sample data. Now, how are you able to apply this, or how can you apply this in the area or the space of health sciences? You see, sometimes, for example, sometimes our health sciences students or our health professionals, sometimes you are working with a larger population. Let's assume that you have a population of a hospital to be 500 patients. 500 patients in a hospital. 500 patients in a hospital. Let's assume we want you to calculate their mean SpO2. Now, what that means is that you have to go around. If the hospital is made up of departments, you have to go to all the departments, enter all the wards in the hospital, and for each ward, you have to check the SpO2 of all the patients and get all the SpO2 of these 500 patients before you can add all of that together and divide by 500 before you calculate the mean SpO2 of the 500 patients. And that is a lot of work. Apart from it going to take time, you would have to use a lot of resources, and even resources including personnel and then other resources. Okay, but confidence interval calculation is going to allow you, this calculation is just going to allow you to make use of a sample. So example, confidence interval can allow you to use a sample of, let's say, 50 patients. Or it can allow you to use a sample of, let's say, 25 patients. Okay, this calculation will allow you to use a sample of either 25 patients or 50 patients, or any other different sample number. Let's say 60 patients, 20 patients. It will allow you to use a sample, not necessarily the entire population. Then you do your calculation, you calculate the mean SpO2 within the sample. But at the end of the day, you are going to get two different means using the sample. Okay? And if in case someone also decides that, okay, for me, I have time and I have the energy, I have the resources, I want to use the entire population. At the end of the day, the mean that's the two values that you had using the samples, the person that decides to also use the entire population will get a certain mean that will fall within the two answers you had from the confidence interval. Okay, so simply confidence interval, another example. Let's do another example. Let's say we have 1,000 students applied for a program. 1,000 students applied for a program. and they wrote an exams over 10 and exams over 10. Now, at the end of the day, let's say we want to know the mean exam score of all the 1,000 students. What that means is that we now have to mark the scores of all the 1,000 students, add all the scores together, and divide by 1,000 before we get the mean score of the 1,000 students. And that is a lot of work. Now, confidence interval can just allow you to select, let's say, 40 students out of these 1,000. Then you just calculate the mean score of just the 40 students. But at the end of the day, this confidence interval statistics will give you two sets of values. One of the values, so let's say it will give you two sets of values. One of the values, let's say 7 to let's say 9. So let's say the confidence interval can land you something like Ci is equal to 7 to 9. And if someone also decides that, okay, for me I have time, I want to actually use the 1,000 students and use their scores to calculate the mean, the answer you get from using this statistically would be or would fall within this range you had from the confidence interval. That is confidence interval. So that means that in confidence interval statistics, in confidence interval statistics, you are going to work with a sample. Okay, so in confidence interval, you are going to work with a sample. Is that okay? That is the first thing that you have to know. In confidence interval statistics, you'll be working with a sample. But after working with a sample, the final confidence interval you are going to get, you use it to make an inference to a population data. Is that okay? That is the first thing, one thing that you have to note in confidence interval. So as health professionals, why is confidence interval important? Confidence interval is very important when it comes to decision making. Because you see, sometimes you need to you are handling a larger population in the space of health system research, okay, and in the space of administering interventions and other things. You are handling a larger population, and sometimes you want to understand, certain variables within the population to make a decision. And because of limited resources in some continents and some parts of the world, sometimes it's going to be difficult, okay, dealing with a larger population. Okay, confidence interval will allow you to work with a sample from the population. You go, and you still get values that actually applies in the larger population. Okay, so this type of statistics is very important when it comes to decision making. And that means that, especially when it also comes to evidence-based research, this type of statistics is also very important when it comes to evidence-based research. Is that okay? Now let's look at the components of confidence interval. The components of confidence interval. The components of confidence interval. Now with the components of confidence interval, we have what we call the point estimate. We have the point estimate. The point estimate can be the mean. We can also have proportion. Because the confidence interval, sometimes you are working with proportion, sometimes you are working with mean. Okay, from the sample. Okay, mean from the population. Now we have the standard error. We have the standard error. We also have the margin of error. We also have the confidence level. And usually, anytime you have confidence level, it means you also have significance or you have the alpha level. Okay, then we can also have what we call probability values. Is that okay? So these are the components. So when we say components, we are looking at the various concepts you are going to look at when you are doing confidence interval. Is that okay? So in confidence interval, you come across this concept, the point estimate. That is the mean, meaning you'll be using mean from a certain population. You also come across standard error. You also come across margin of error. You come across what we call confidence level. You come across what we call significance or alpha level. And you come across what we call probability values in confidence interval calculations. Is that okay? Yes, and when you are doing confidence interval, you are going to also use distribution tables. So the distribution tables with confidence interval, you are going to use the T distribution. You are also going to use the Z distribution table. Is that okay? Yes. So these are the various components of confidence interval. The point estimates, we have the standard error, we have the margin of error, we have the confidence level, the significance or alpha level, we have the probability values, and then we have the distribution tables. Now quickly, let's look at the various confidence interval formulas. Okay. Now we have two formulas that are commonly used. For today's video or section, I'll introduce you to two common formulas that are used in confidence interval calculations. Okay. Now the first formula, I call it the Z distribution formula. Okay, the first formula, I call it the Z distribution formula. Okay, the Z distribution formula. Now with the Z distribution formula, this is how you state the formula. Ci is equal to mean plus or minus Z score multiplied by standard deviation all over square root of n. Is that okay? So this is the first formula for the Z distribution formula. This is the first formula. I call it the Z distribution formula. Confidence interval is equal to mean plus or minus Z score multiplied by standard deviation all over square root of n. Now the second, under the first formula, you can say or Ci is equal to mean plus or minus Z score multiplied by standard error, or Ci is equal to mean plus or minus margin of error. Okay, so these are the various formulas for confidence interval. This is the first formula. We call it the Z distribution formula. Some literatures will say the Z score formula. So what's the Z score formula? Confidence interval is equal to mean plus or minus Z score multiplied by standard deviation all over square root of n. Or confidence interval is equal to mean plus or minus Z score multiplied by standard error. Or confidence interval is equal to mean plus or minus margin of error. Okay. Now, the key point you have to note over here is that we use this formula when the sample size is 30 or large. Keep it in your mind. We use this formula when the sample that you are working with is 30 or large. So take notes that we use this distribution formula when the sample into bracket n is 30 or greater than 30. When sample is 30 or greater than 30, that is when we use this formula. Okay, when sample size is 30, let me do it this way, 30 or large. So the first formula of confidence interval calculation, we call it the z-distribution formula. Confidence interval is equal to mean plus or minus z-score multiplied by standard deviation all over square root of n. Or confidence interval is equal to mean plus or minus z-score multiplied by standard error. Or confidence interval is equal to mean plus or minus margin of error. Use this formula when sample size is 30 or large. So anytime the sample size you are handling is 30 or more than 30, you use the z-distribution formula. But now let me take you through the dynamics of this formula. Now, if you look at this formula, this part of the formula here, this part of the formula, the standard deviation over square root of n. In statistics, we call it the standard error. Okay, the standard deviation all over square root of n, we call it the standard error. That is why when we were looking at the components, I told you that one of the components of confidence interval is the standard error. So this portion of the formula, we call it the standard error. Now, it's important that you know what each part of the formula represents, because in a test, we can ask you to just calculate for the standard error. So the standard error is equal to standard deviation all over square root of n. Standard error is equal to standard deviation all over the square root of n. So this part of the formula, we call it standard error, SE. Is that okay? So that is why if you check the second formula, CI is equal to mean plus or minus z-score multiplied by SE. This SE is the same as standard deviation all over square root of n. Okay, now this part of the formula here, this part of the formula, the z-score multiplied by standard deviation all over square root of n, we call it the margin of error. So when we say margin of error, it's the z-score multiplied by the standard error, margin of error. Or margin of error is the z-score multiplied by standard deviation over square root of n. Okay, for the last time, when we say standard error, this part of the formula is what we call standard error. So how do you calculate for standard error in a z-distribution table? Or when you are working with a sample that is 30 or large, how do you calculate standard error? Standard error is equal to standard deviation all over square root of n. Now, standard error calculation will be different when you are, so in fact, standard error calculation will be similar when you are dealing with what? The z-distribution formula. But we will get over there. But margin of error calculation will be different in the z-distribution formula. And we will come to that later on. Okay, so know the parts of the formula. So the z-score multiplied by the standard deviation over square root of n, that's the margin of error. So this part 2 is also margin of error. Z-score multiplied by standard error. That part also represents margin of error. Okay? Yeah, so when we say, so you see the second formula, mean plus or minus margin of error. Required, because the margin of error is the same as z-score multiplied by standard deviation over square root of n. Or z-score multiplied by standard error is the same thing. Is that okay? So now, in a situation now, the key point is that when will you use this formula? When the sample that you are using in the statistical test is 30 or large. So, and that is the key thing that you check. Okay? So for example, we give you a question and the sample in the question is 30. Or the sample in the question is 40. Or the sample in the question is 50. Quickly, this is the formula you are going to use. We use this formula when the sample size n is 30 or large. Keep it in mind. Now let's look at the second formula before we begin to look at some examples. Let's look at the second formula. But even before the second formula, you see this very formula. Let's write the formula again. Let me write the formula again. Ci is equal to mean plus or minus z-score multiplied by standard deviation all over square root of n. Now you see this z-score in the formula. Now in confidence interval calculation, because it's a statistical test and a hypothesis, usually you are working with a certain confidence level. So all the time the confidence level will be given to you in the question. Now from our previous lessons in hypothesis testing, we discussed the various confidence levels. But the common confidence levels, we have the 90%, okay? We have the 95%, we have the 98%, and we have the 99%. These are the common confidence levels that we can work in statistics. Now, each confidence level corresponds to a certain significant level. The significant level in statistics is what represents the error space or the error margin. Okay, so for 90% confidence, the significant will be 10%. You just subtract it from 100. For 95% confidence, the significant will be what? Will be 5%. For 98% confidence, the significant will be what? Will be 2%. And for 99% confidence, the significant will be 1%. But this is not what we need here. Now, what you should know is that every confidence level also has its corresponding z-score. For example, 90% confidence, the corresponding z-score is 1.645. 95% confidence, the corresponding z-score is 1.96. 98% confidence, the corresponding z-score is 2.33. And 99% confidence, the corresponding z-score is 2.576. Is that okay? And you see, you have to, so in the question, if the examiner tells you that, or you are working with 90% confidence, it means the z-score in the formula, you have to put this 1.645 there. If in your statistical calculation of CI, you are using the z distribution, and you are working with 95% confidence, it means this z-score, in place of the z-score, you have to write 1.96. Okay, if for example in the statistical analysis you are working with 98%, it means here you would have to write 2.33. Okay, so the z-score, what you write here, depends on the confidence level that you are working with, or the confidence level that has been given to you in the question. So if the confidence level given to you in the question is 95, then it means the z-score, when you get to you are writing the formula, you can choose not to write the z-score, then you write the 1.96 there. Okay, it's very good that you memorize this. It makes statistical calculations for you very easy as a student, okay, and also as a statistician. So it's very good that you memorize this, the common confidence levels and their corresponding z-scores. So 90% confidence, the corresponding z-score is 1.645. Okay, 95% confidence, the corresponding z-score is 1.96. Okay, 98%, the corresponding z-score is 2.33. And then 99%, the corresponding z-score is 2.576. So memorize them. But let's look at what if you forget it in the exams. What if, let's say, in the exams, you have forgotten how, for example, let's take the 95% confidence level. 95% confidence level. We know the corresponding z-score is 1.96. Let's say in the exams you have forgotten how they came by this 1.96. You've forgotten that the corresponding z-score for this is this. What are you going to do? What you are going to do is that, now the 95% that has been given, 95% means 95 over 100. 95% means 95 over 100. Now this 95 over 100 divide, write it in the form of decimal, or proportional probability. So you are going to get 0.95. 95 over 100 is the same as 0.95. You just convert it to decimal. It will be 0.95. Now when you get by the 95%, when you subtract from 100, you get 5. It means the significance for this is 5%. 5%. 5% also means 5 over 100. And that is also equal to 0.05. Now another thing that you have to note is that confidence interval calculation is a two-tailed test. Keep it in your mind. Confidence interval calculation is a two-tailed test. Now, why is it a two-tailed test? It's a two-tailed test because in confidence interval calculation, we are comparing two means. You know, usually in confidence interval, you see we have two answers. So we are making a comparison in a population too, and a comparison in a sample. And again, we are comparing two means. So it's a two-tailed test. Now, if you have a two-tailed test, okay, the confidence goes in for the sample you are testing, but the significance, you share it for the various sites. So what that means is that this significance of 0.05, you have to divide it by 2. Now when we divide this 0.05 by 2, we are going to get 0.025. When you get this 0.025, come and add it to the confidence probability. So you are going to get what we call 0.95 plus 0.025. When you add this together, you are going to get 0.975. Now when you get this 0.975, go straight to, we have a distribution table we call the Z distribution table. If you are learning confidence interval, get that table, download it, it's available online. So you go to the Z distribution table. Now on the Z distribution table, you see the Z values are here. The Z values are on this side. Okay, you see the Z values are on this side. And then you trace, but remember, even though it's a two-tailed test, you divide it by 2 to get this. But the significance you still have to work with is the 0.05. So you look out for the Z, then you look out for the 0.05 on the significant level. So if you have the Z distribution table, you see the Z values are on the left, the right side, and then the significant values are on the top, the uppermost. So you look out for the Z value, then you look out for this. Now, when you stand on the significance, start looking for a probability, the probability that is similar to this. The probability similar to this. Okay, in looking for it, you will come and meet 0.9744. And then you will also come and meet 0.9898. Something like this. 0.9744 and 0.9898. You come and meet these two probabilities. Now, this one is not the same as this. So what that means is that the value is in between these two probabilities. It's between 0.9744 and this. So you trace this to the Z, you come and meet 1.9. You trace this to this side, you would also come and meet 2.0. So what that means is that the Z value for this probability is between 1.9 and then 2.0. Now, but you see, statistically, you see the common values, the calculated one, the automatically calculated one that you are recommended to memorize is 1.96. Now, let me explain that to you. You see, if you check the probability, this last end is 0.975. This one, assume it as 75%. What that means is that in between the 1.9 and 2.0, the probability is more closer to the 2.0. Okay, so let's assume you have no idea about this, it being 1.96. You can even consider it to be, but you see, the 75% closer. So you can't assume it to be the middle will be 1.95. You can't assume it to be exactly the middle. Okay, so at least you can add something to the middle. Okay, and in per assumption, if you are adding something to the middle, you can choose to do 1.962, 1.964, 1.965, and that is going to tell you where the answer is. That's how you get it. Is that okay? So, but then this is how, so you can use this in case you couldn't memorize the values. You can go through this process and you still get the Z values. Okay, so these are the Z scores. Okay, so in case you get the process, you can go through this same process. Okay, so let me just go over it for the last time for you. Okay, yeah, so I mentioned that if the examiner tells you to use 95%, 95% is the same as 95 over 100. And 95 over 100 is the same as 0.95. Now this 95%, the significance is 5%. 5% is also the same as 5 over 100. And 5 over 100 is the same as 0.05. Now confidence interval calculation is a two-tailed test. Why is it a two-tailed test? It's a two-tailed test because we are comparing two different means from the sample and from a population. Okay, and again, you're also going to get two values. So it means that the error has to be shared to the different means that you are working with. So you have to divide the significance by 2, the error by 2. Okay, so you are going to get 0.025. Then you add this probability from the error, the slated error, you add it to the confidence probability. So you add it, you are going to get 0.95 plus 0.025. Now this is going to give you 0.975. When you get this 0.975, take it to the Z table. Take it to the Z distribution table. On the Z distribution table, what you have to take note is that when you are taking this probability to the Z distribution table, be mindful of the significance. That the significance still remains this. So you are going to look for this 0.05 on the Z table at the top. Now when you stand on it, start reading and observing the probability values until your target is this. But you don't come and meet exactly this. You come and meet 0.974. And you should know, because this is 5, you should know that this one is bigger than this. So you don't settle on this, you move on to the next. But the next one you move to is also bigger than it. So what it means is that the probability is in between these two probabilities. So it's somewhere here. Okay, but what you have to do is that trace this probability to the Z score. It will fall on 1.9. Then you trace the next one to, it will fall on 2.0. Okay, then now you come and check the probability. See, the probability is in 3 decimal places. Now the last 3 is giving you an idea. The 75, 0.9, the 75 is telling you that, see it as 75%. So it's telling you that in between this Z score and this Z score, the Z score is more closer to the 2. It's 75% more closer to the 2. That's the meaning. Is that okay? So let's assume the middle is 1.95. And we are saying it's 75% closer. The 1.95 is 50%, meaning halfway. So 75%, meaning you have to add something small to the point. So it will be something like 1.96, 1.97, something like that. And you don't go beyond the 7. You don't go to get to exactly 2. Is that okay? And that is how the Z score for 95% confidence is 1.96. You can use this same process to go through and derive the Z score for 90, Z score for 99, Z score for 90, and Z score for 90. The same thing. You can use this same process. You end up getting all these Z scores from the Z table. Is that okay? Yes, with that being said, now let's look at our first application. Or before we even look at our first application, let's look at the second formula first. Let's look at the second formula. Now the second formula, we call it the T distribution formula. So the second formula, we call it the T distribution formula. Example, the second formula, we call it the T distribution formula. Now, what is the T distribution formula? With the T distribution formula, Ci is equal to mean plus or minus T alpha over 2 by dn multiplied by standard deviation all over square root of n. Okay, or Ci is equal to mean plus or minus T alpha over 2 by into brackets n minus 1 close the bracket multiplied by standard deviation all over square root of n. Or confidence interval is equal to mean plus or minus T alpha over 2 by into brackets by df multiplied by standard error. Okay, this is what we call the T distribution formula. So the T distribution formula, Ci is equal to mean plus or minus T alpha over 2 by df multiplied by standard deviation all over square root of n. Or Ci is equal to mean plus or minus T alpha over 2 by into brackets n minus 1 multiplied by standard deviation all over square root of n. Or Ci is equal to mean plus or minus T alpha over 2 by df multiplied by standard error. Okay, now let's look at the various parts of this formula or components of this formula. So here is the mean. This is plus or minus. This one we call it T alpha over 2. This alpha here represents significance. Now, the confidence level for the calculation will be given to you in the question. The examiner can say the confidence level is, let's say, 95. When the examiner tells you the confidence level is 95%, it means the significance is 5, which is 5 over 100. 5% is the same as 5 over 100, and that is 0.05. Okay, so it means that it's T 0.05 over 2. That's the meaning. That's what we call the T alpha over 2. Now, the T alpha over 2 will depend on the confidence level that the examiner will give to you in the question. Okay, so the T alpha over 2 will depend on the confidence level that the examiner. So if the examiner tells you the confidence is 5%, 5% means significance is 100, and then 100 significance is 5%, and then 5% is the same as 5 over 100, and that is also the same as 0.05. So, and this 0.05 is what we call the alpha. That is what we have in the formula. So the T alpha over 2, it simply means T alpha over 2 is the same as T 0.05 over 2, and that's also the same as T 0.025. Is that okay? If you divide this one by 2, you get 0.025. That is what you have over here. Okay. Now the df. In confidence interval calculation, if you are asked to calculate df, in confidence interval, df is equal to n minus 1. df is equal to the sample size minus 1. That's the formula for df in confidence interval calculation. Remember the formula for df in chi-square testing. Chi-square hypothesis testing is different. Okay, that's into bracket rho minus 1, close the bracket, open the bracket, column minus 1. That is different from this. Okay, here we are looking at confidence interval calculation. So df is equal to the sample size minus 1. Is that okay? And that is why if you check this second formula, you see the second formula, mean plus or minus T alpha over 2 by n minus 1. This n minus 1 is the same as df. Is that okay? And remember, in a statistical question, we can give you a question and we will just ask you to calculate the df. What we are going to do is you just concentrate and look out for the sample and just subtract 1 from the sample. That's all. You have your answer. Okay, again, you see, I told you in the beginning that when you are looking at the Z distribution formula or the T distribution formula, the standard error formula remains unchanged. It's the same. The standard error is the same standard deviation over square root of n in Z distribution, and it remains the same also in T distribution formula. Is that okay? So this is what we call the T. So over here too, this part of the formula is the SE. And this part of the formula here, this whole part of the formula is also the margin of error. Is that okay? So this whole part of the formula is the margin of error. This part of the formula is the SE, the standard error. And just this part of the formula here alone, it will give you the T value. Is that okay? So this whole part of the formula is the margin of error. This part of the formula alone is the standard error. And this whole part of the formula is going to give you the T value. Is that okay? So that is the part of the formula. And in an exam, we can give you. Now, let me add a condition. Note. You use this formula when sample size is less than 30. Listen carefully. You use this formula when sample size is less than 30. Okay, keep it in your mind that we use this formula when sample size is less than 30. So the T distribution formula for confidence interval calculation states that confidence interval is equal to mean plus or minus T alpha over 2 by df multiplied by standard deviation all over square root of n. Or confidence interval is equal to mean plus or minus T alpha over 2 by into bracket n minus 1 multiplied by standard deviation all over square root of n. Or confidence interval is equal to mean plus or minus T alpha over 2 by df multiplied by standard error. Use this formula when sample size is less than 30. So remember, we use the Z distribution formula when sample size is 30 or large. We use the T distribution formula when sample size is less than 30. Okay, so in a statistical calculation of confidence interval, one of the key things we concentrate on is the sample size. Because the sample size that would determine which of the distributions or which of the formulas you have to use. Okay, so now let's look at our first question. So today we will just go through two questions. One for the Z distribution formula, and then another question also for the T distribution formula. So today, that is what we'll be doing practically for today. Okay, so let's look at our first question. I'm reading the question to you. Okay, so we have a sample of 49 women. A sample of 49 women has a mean daily steps of 6,750. A sample of 49 women has a mean daily step of 6,750. Standard deviation is 1,500. Calculate the 95% confidence interval of the mean. Okay, so you see in the question, the examiner have given you a sample of 49 women, meaning the sample size n is 49. It will be given to you all the time in the question. That is the first parameter we have in the question. Now the examiner says that they have a mean daily step of 6,750. So the mean in the formula will also be given all the time in the question. Now the next thing is that standard deviation is equal to 1,500. You see the standard deviation has also been given. You know you need the standard deviation in calculating for the standard error. And also you need a standard deviation in calculating for the margin of error as well. Good. Now, the next thing is that calculates the 95% confidence interval of the mean. So now, what are you going to do? You write analysis. Analysis. So you have a question like this. The first thing you write analysis. And you write sample size into bracket n. What was the sample size in the question? 49 women. Okay, you check the question again. What's the mean? The mean daily scale is 6,750. Standard deviation is 1,500. Now, what's the next thing you have in the question? Confidence level. Okay, the confidence level is what? It's 95% CI. Sorry, 95%. There's the confidence level that has been given in the question. Is that okay? So these are the parameters we have in the question. Now, when you have a question like this, what's the first thing you check? You check the sample size first. Check the sample size, the n. Check the n first. Why? It's the n that will inform you which of the formulas you use. So here the n is 49. So which formula do we use? We use the z distribution. Why? We use the z distribution formula when sample size is 30 or large. This one is more than 30, so it means we use the z. So you write your formula. Ci is equal to mean plus or minus z score multiplied by standard deviation all over square root of n. Okay, then now you check. I told you the z-score. The examiner will not give you the z-score most of the time. You have to know the confidence level. The examiner will always give you the confidence level. Or the examiner can choose to give you the alpha or the significance. Okay, if the examiner tells you in the question that calculate the CI at a significance of 5%, it means the confidence level is 95%. It's the same. But most of the time, the examiner is going to give you the confidence level in the question. In this case, the confidence level is 95. Now, then you remember that the common z-scores, 90 is equal to 1.645, 95 is equal to 1.96, 98 is equal to 2.33, 99 is equal to what? 2.576. So this is what we are going to use to work, because this is what the examiner gave in the question. This. Okay, then you kind of put this 1.96 into the formula. So what it means is all the time you have to memorize this. It's two things. Either you are memorizing this or you are learning how to derive the scores yourself. And I've explained all of that before we got here. Okay. Good. So Ci is equal to mean plus or minus z-score. Then you have to write it again. Ci is equal to mean plus or minus. The z-score is 1.96 times standard deviation all over square root of n. Now, the next thing you are going to do is that, remember, when you are doing confidence interval calculation, do it from behind and come forward. So do the standard error first. So you write, the standard error is this. So it means calculate the standard deviation over square root of n first. So you are going to get SE is equal to standard deviation all over square root of n. What did we get for the standard deviation? The standard deviation is 1,500 divided by, what did we get for the square root of n? The square root of 49. That would be 7. So 1,500 divided by 7. That is going to give us 214.285. You are going to get this. Okay, so this answer represents the standard error. It represents this alone. It represents this, the standard error. Now, after getting the standard error, multiply the standard error by the z-score, and that is the margin of error. And you come and write NE, that's margin of error, is equal to 1.96 times 214.285. So you multiply the margin of error you multiply the z-score by the standard error, you get the margin of error. You multiply the z-score by the standard error, you get the margin of error. You multiply the z-score by the standard error. So that should tell you that we can give you this same question, and the examiner will just ask you to only calculate for the standard error. We can give you this same question, the examiner will only require you to calculate for the margin of error. And at the same time, we can give you the question you'll be required to calculate the complete confidence interval. Okay, so after you've gotten this, then you can write Ci is equal to, what is the mean in the question? Now that we are calculating the confidence, the mean is 6750 plus or minus, then you put the margin of error answer there. What is the answer for the margin of error? The answer is 420.000. So 420. Okay. Now when you get over here, so it means we have the mean times the rest of the part of the formula. Okay, that is what we have. So this is representing the margin of, this is representing the mean. Is that okay? So when you get over here, you write it, but you see, look, anytime you are doing a statistical and mathematical calculation and you see plus or minus, it means you are supposed to get two answers. Plus or minus. All it means is you are supposed to get two answers. You have to derive an answer for the minus side, and you have to derive an answer for the positive side. So you are going to have what we call lower Ci. The lower Ci is the side for the minus. Okay, so the lower Ci will be 6750 minus 420. Then you have the upper Ci. The upper Ci will also be 6750 minus 420. That's the upper Ci. So we have the lower Ci, which is 6750 minus 420. Then we have the upper Ci, 6750 minus 420. Okay, now, so you do the computation for the lower Ci. When you do the computation for the lower Ci, you are going to get 6330. When you do the computation for the upper Ci, you get 7170. So these are the answers we've gotten. When you get to that, you write, therefore, 95% confidence interval, 95% Ci is equal to, into brackets, 6750, comma, 7170. So you see, the bracket, what do we have? We have the answer for the lower Ci, and then the second part is the answer for the upper Ci. Now when you get over here, you are not done. In fact, in confidence interval calculation, the most important aspect is what we call the interpretation. The interpretation. In confidence interval calculation, the most important aspect is what we call the interpretation. Now, how do we write the interpretation? This is how we write. We are 95% confident that the true mean daily steps in the population lies between 6750 and 7170. This is how we write the interpretation. Remember, when we are doing the upper Ci, we use the plus. So you see the lower Ci is for the minus. The upper Ci, you have to use the plus. Okay? Yes, so you have to put the plus over there. Okay, so yes, so all the time too, another trick is all the time the upper Ci, the answer have to be greater than the lower Ci. That is also another trick. So this is how we write the interpretation. We are 95% confident that the true mean daily steps in the population lies between 6750 and 7170. Now, how do we do the interpretation? This is how we do the interpretation. In your interpretation, you have to emphasize on the confidence level that was given. So you see in our question, the confidence that was given is 95%. All the time, you have to start it with we are. Okay, then the confidence that was given in the question is 95. If the confidence that was given in the question is 98, it won't be we are 95, it will be we are 98% confident that. Okay, now again, in writing the interpretation, you also have to pay attention to the variable you are dealing with. Here, the variable we are dealing with in this question is daily steps. Okay, so you see, 49 women has a mean daily steps. So what we are dealing with is daily steps. Let's assume what we were calculating the confidence interval for is fasting blood sugar. That is a minimum per liter. Okay, so it will be we are 95% confidence that the true mean fasting blood sugar in the population. So in writing the interpretation, one, you have to know the confidence level that was given. Two, you have to pay attention to the variable you are working with. And you also have to ensure that this word population appears in your interpretation. If this word population does not appear in your interpretation of confidence interval, it's practically incorrect. This word population has to appear in your interpretation of confidence interval calculation. Okay, so for example, let's say you are calculating CI for SpO2, and then you have 95 to, let's say 90, you have 95 to 98. Okay, and the confidence that was given is 99%. It's simple. We are 99% confident that the true mean SpO2 in the population lies between 95 and 98%. You always have to add the unit. Let's assume that this one, you see, you have to make sure, you see this one, we didn't use 95, we used 99. Because the confidence that has been given or we are dealing with now is 99. Let's assume we are dealing with diastolic blood pressure in a certain sample. And we use it to do the confidence interval, and we had, let's say, 80 to 95. And then the confidence we are working with is, let's say, 90. And we ask you to write the interpretation. We are 90% confident that the true mean diastolic blood pressure in the population lies between what? 80 and 95 millimeters of mercury. So the point is that when you are writing the interpretation, take note of the confidence level, take note of the variable, and take note of the word population. All these are things that have to be seen or featured when you are writing the interpretation. Okay, good. So now with this, let me explain the calculation that we've done. So when we give you the question, first of all, you write analysis, and the analysis write all the parameters that has been given in the question. We have the sample. What is the sample? N is 49 women. The mean is 6,750. Standard deviation is 1,500. Confidence level is 95%. Now, confidence interval. Now, once you've gotten these parameters, pay attention to the sample. The sample is 49. Meaning, the formula you have to use is the Z distribution formula. Why? Because we use the Z distribution formula when the sample size is 13 or large. So here, the sample size is 49. It's greater than 30. So you write the formula. CI is equal to mean plus or minus Z-score multiplied by standard error. Okay, where do you get the Z-score? The Z-score will depend on the confidence level that was given. If the confidence is 95, it means the corresponding Z-score is 1.96. Then you come and put that in place of the formula. So the formula will now be mean plus or minus 1.96 multiplied by standard deviation all over square root of n. Okay, then and I told you that when you are doing the calculation, you calculate from behind forward. So which part of the formula do you calculate first? The standard deviation over square root of n, and that is what we call the standard error. And the reason why you have to learn how to calculate. Some students may want to write all at once and calculate. It's not a problem. But if you try doing that all the time, you may not develop the skill of learning how to calculate for the standard error alone. And so if you learn it that way by just writing all together, if we end up asking you to just calculate for the standard error, you will not know how to go about it. So calculate it separately. So you do the standard error and you finish, put the answer there. You come and calculate for the margin of error. How do you calculate for the margin of error? The answer you have for the standard error multiplied by this. So you see here, when you calculate for the standard error, you have 214.285. Okay, now after getting that, now the margin of error, how do you get it? You multiply the z-score, which is the 1.96, by 214.28, then you have 420. So this 420 represents the margin of error, this. It represents this. So what it means is that you now know the mean. The mean is already in the question. Here is the, it will always be given to you in the question. Okay, so you write the mean. So the mean plus or minus, and that is what we have here. So CI is equal to the mean. This is the mean. 6,750 plus or minus 420. Where is the 420? That's the margin of error. Okay. Then after you've gotten here, this one should inform you that anytime you are doing statistical calculation, you come across plus or minus. It means you have to definitely get two answers. So you do the answer for the lower part, but here because you are doing CI, the lower part you call it the lower CI, and the upper part you call it the upper CI. The lower part is just the part that you are using the subtraction. The upper part is the part you are using the addition. So lower CI is equal to 6,750 minus 420, which is equal to 6,330. The upper CI is equal to 6,750 minus, plus, here is plus 420, which will give us 7,170. Now another trick that should guide you is that all the time the upper CI answer have to be greater than the lower CI. And again, when you get to this point, after you are done with this, let's assume, you see here, we didn't get any decimals. Let's assume in our calculation we have 6,330.482. And here we have 7,170.567. When you get something like this, when you are going to write the answer in the list last but one stage, 95% CI is equal to 6,000. You have to convert these decimals into two decimal places. In confidence interval calculation, if the answer you get is in decimals, we convert it to two decimal places before we write the final answer. Okay, but you see here, this one we have overvalues, so we don't do any conversion over here. But keep it in your mind. Let's assume we had decimals, and the decimals, when you are working, work with three decimal places. When you get to the final answer, convert it to two decimal places before we use that to write the last but one answer. And also before you use it to write the interpretation. Keep that in your mind. It's a principle. Is that okay? So yeah, so you write 95% confidence is equal to, you write the answer. The lower one will come first. If you come and write the 7,170 first before comma, the second one is wrong. The lower CI first and the upper CI second. Because of that, be guided, do the lower CI calculation first before you come and do the upper CI calculation. Okay, now let's look at our last example for today's session. And the last example, we focus on the t-distribution example. Now before we look at our last example, let's write the formula for the t-distribution. So mean CI is equal to mean plus or minus T alpha over 2 by df multiplied by standard deviation all over square root of n. Okay, so let's take our first question. Let's take our first question for the t-distribution. Now, the mean potassium level of a sample of 20 patients is 4.2 millimole per liter. Standard deviation is equal to 0.6. calculate the 95% confidence interval of the mean. The mean potassium level of a sample of 20 patients is 4.2 millimole per liter. Standard deviation is equal to 0.6. Calculate the 95% confidence interval of the mean. So now let's go to the drawing board. Now I told you that when we give you a question like this, the first thing that you do is that write the parameters that has been given down. So after stating the analysis, you write the parameters down. Okay, so what parameters do we have? You write the sample first. So the question says the sample is the n. The question says the sample is 20 patients. 20 patients. Now the next thing is that the mean population level of a sample of 20 patients is 4.2 millimole, meaning the mean is equal to 4.2 millimole per liter. Okay, the next parameter is that standard deviation is 0.6. SD is equal to 0.6. Standard deviation is equal to 0.6. Okay, now the next statement is that calculate at 95% confidence interval. Calculate the 95% confidence interval of the mean. So what it means is that confidence level is equal to 95%. So calculate the 95% confidence level, so a confidence interval of the mean. So this is it. So I told you that anytime we give you a question like this, the first thing you have to do is that look out for the sample. You see here the sample is 20. Now the sample being 20 tells you that you have to use the T distribution formula. Why? The principle says that use the T distribution formula when sample size is less than 30. And this sample size is of 20. Meaning we have to use the T distribution formula. Why? It is less than 30. So quickly you write the formula. Ci is equal to mean plus or minus T alpha over 2 by df multiplied by standard deviation all over square root of n. Then you write the formula nicely. So mean plus or minus T alpha over 2 by df multiplied by standard deviation all over square root of n. The same principle here, you do the standard error first. So you do SE is equal to standard deviation all over square root of n. What's the standard deviation from the question? 0.6 over square root of n. What is n from the question? N from the question is 20. Then you compute this. When you compute this, you are going to get 0.1342. You get 0.1342. So we've done this part. When you finish, calculate the df. Okay, or let's take this part of the formula. Let's take this part of the formula. If you remember, when we were looking at the components of the formula, I told you this part of the formula, we call it the T value. The T alpha over 2 by df. So let's take it here. Let's bring it here. T alpha over 2 by df. Now this df is equal to n minus 1. In confidence interval calculation, this df is n minus 1. So the n is 20 minus 1 is 19. So what it means is we are going to get 19 over here. This alpha here is the same as significance. But the significance, how do you get the significance? You derive it from the confidence given in the question. The confidence is 95%. So what it means is significant is 5%, which is also equal to 0.05. So this is the alpha. This is what we call the alpha. So it will become like this: T 0.05 over 2. And 0.05 over 2 is also equal to T 0.025 by 19. Now when you get this, you quickly take this to the T distribution table. Take to the table. T table. Take this to the T distribution table. On the T distribution table, you are going to see the DF on the right side of the table. The DF will be lined up on the right side. And then the significance will be at the top. Now, the significance, you are going to remember, even though you divided the significance by 2, why? It's a two-tailed test we are doing. But you still use the same significance. And again, for T distribution, where you would have the significance 0.05 is the same area that you would have the significance of 0.025. It's the same. So you will check the significance where at the top of the table where we have 0.025, at the same time we have 0.05. You check at the top of the T table where we have this, okay, and this at the same time. So you check where we have this 0.05. So you check where we have 0.05 and 0.025 at the same time. Then you come and trace where we have DF90. You come and look, so you stand on where we have DF90 and look out for where we have 0.05 and 0. And trace where they meet. You notice that on the T table, they will meet at 2.093. If you check very well, you notice they will come and meet at 2.093. All it means is that the T value is 2.093. Is that okay? Good. So this whole part of the formula here, this whole part of the formula, the answer is 2.093. Okay, so now you can now calculate the margin of error. So margin of error is equal to 2.093 times 0.1342. NE is equal to, then you do the calculation. So NE will be equal to 0.28088. So that's the answer you get from the NE. Now when you get the answer for the ME represents this part of the formula. From the T alpha over 2 by DF multiplied by standard deviation over square root of N. And we have the mean in the question already. So CI will be equal to the mean, what we have, 4.2 millimole per liter, okay, plus or minus the margin of error 0.28088. Now, after you've gotten here, you now do the lower CI. What's the formula for the lower CI? The lower CI, you just do, is going to be 4.2 minus 0.28088. Then you get the upper CI